Good morning, everyone. Today is the last day of our workshop, unfortunately, because we have had many interesting talks, but today will not be different. We start this morning with a short course by Peter Müller. Dr. Müller is professor at the University of Texas at Austin. He is an elected fellow of the International Society Bayesian Analysis, the American Statistical Association, and the Institute of Mathematical Statistics. Also, he has been awarded the Zellner Medal. He has a long and beautiful career, and unfortunately, I cannot say everything he did, but I will summarize that he authored more than 210 scientific publications, 10 books, and edited volumes, and has served on editorial board of 3 scientific journals and technical series. Peter, it is a pleasure to receive you again here, and please, you start when you feel able.
Thank you. Obrigado. Bom dia. I could have simply summarized, Peter is old. That's the sufficient statistic. So thanks for joining this morning for some comments on non-parametric Bayes. I prepared for about 2 hours. We plan to make a stop somewhere in between for a few minutes just to take a breath. Please stop me anytime when you have questions. Podem fazer perguntas in Portuguese, devagar, and I'll try to understand or somebody translate. So please feel free to ask slowly in Portuguese, just unmute and ask. So I want to tell you a little bit about non-parametric Bayesian inference. Here in the title slide, you can already see a quick summary of what it is about. Non-parametric Bayes, a lot of non-parametric Bayesian inference is about random probability measures, means putting prior probability models on unknown distributions. You see there on the left side, there's a distribution on the integers here. The pins represent something like the empirical frequencies. The empirical frequencies are missing for the 0 because it's about counts. When you have a 0 count, you don't see it, it's missing data. Anyway, the pins represent the data, and then those gray spaghetti, those are draws from the posterior random probability measure that we put on these integers. The integers are connected just for display. It really only is relevant at the actual integers. So it's about probability models on random distributions that can be about density estimation, as in the left picture. It could also be applied inside a bigger hierarchical model. In a bigger hierarchical model, you often have a notion of random effects. The right panel shows inference for random effects. Random effects, in my mind, is just another application of density estimation. Again, it's about inference for a distribution, in this case, distribution not of observable data, but distribution of random effects. Each of the dots here corresponds to one observation. Each of the dots is linked with one observation. Those are observation-specific random effects. Typically for random effects distribution, like in a mixed effects linear model, we might assume multivariate normal distributions. Can you see that using a multivariate normal distribution in this example would really miss a lot of the features here? Like there's multimodality, there's this funny shape here in the left lower corner. We would miss all that. If we were to use a multivariate normal distribution, we would probably just get like some very rough approximation. Especially in this application, that would be critical because without telling you details of the application. What matters is locating the random effects in one of those 4 quadrants that are formed by the 2 lines. And can you see that if we were to replace the actual distribution that you can eyeball from the dots here, if we were to replace it just by 1 multivariate normal, for many observations, we would misjudge which quadrant they fall into. So to formally do inference about these unknown distributions, we need prior probability models on the random distributions, and that's what we shall talk about. You can get verbatim copies of the slides from this URL that's highlighted at the bottom of the slide. I try to prepare not too many slides so we can go slowly and have time to talk about things. Quick outline. Non-parametric Bayes in general is about, like, it's more general than density estimation and random distributions. In general, it's about probability models on infinite dimensional unknown quantities. But the main application, I think, is the density estimation. So we'll talk a bit more about that first. An application of density estimation is when you estimate not the density, when you estimate not the distribution of the observable data, but rather a distribution of hypothetical latent quantities known as random effects. So we talk about random effects distributions. But then another application of prior probability models on infinite dimensional quantities arises in non-parametric regression. So at that moment, the unknown quantity could be the regression mean function or more, and we'll talk about that. So that's our second big topic, and that's all I plan to do. That should keep us busy for the next short 2 hours. So perhaps best to start with an example, just to motivate what's going on. This example is about inference for a clinical trial, inference for a study. That study enrolls patients who went through some lung surgery on the lung. And some of these patients develop leaks in the lung. I think of it almost like rupturing your bicycle tire. Like if as a part of the surgery, it could happen that you get leaks in the lung. And then it takes time until they resolve. Our data is the time until resolution of air leaks in the lung after lung surgery. We are comparing, like, patients are assigned to 2 treatments. So we want to compare 2 treatments, standard of care, which I think is simply essentially doing nothing, just waiting until that naturally heals, versus the alternative, which is some sealant named Progel. I don't know what exactly it is. It's just some medication that is meant to speed up the recovery. And so what we really want to do is we want to compare time to reduction of the air leak between standard of care versus the new treatment. And one of the complications here is, maybe let me jump ahead to a figure. I have a figure further down. Oh, here's a figure already. That figure on the right side, that shows hypothetical distributions of the G.E.P. In black, you can see a distribution under standard of care. Can you see the way how this looks? The time axis is days. So some patients, it might take up to 40 days, beyond 1 month, until they fully recover. Most patients recover within the first 10 days, including some who almost immediately recover. So the black one could be under standard of care. And the red one might be hypothetically under the new treatment. Can you see the red distribution has one funny feature? There's a huge atom. There's a point mass at 0. So there's a point mass at 0. Other than that, it's maybe with a bit of fantasy, you could see it slightly shifted towards smaller values. But this is what the distribution might look like under the experimental therapy. Now, in comparing we want to compare these two distributions. In comparing these two distributions, one important feature is that the value of an improvement early on is much higher than the value of an improvement later on. In the following sense, if the time is 0, t equals 0 means these patients do not need to stay in the hospital. They can immediately go home. So moving from t equal 1 to t equals 0 has a much higher utility than moving from t equal 31 to 30. Whether you're 30 days in the hospital or 31 days in the hospital, it doesn't really matter that much. Whereas 1 day versus 0 days makes a huge difference, because it's a difference between having to stay overnight versus not. Which already points us to the fact that just comparing means will probably miss the important features of the difference. The most important feature of the difference between the two distributions is that there's much more probability mass here in the early part. And that shift of probability mass is really important. Same thing in other words, it's not just the overall mean that matters, but it's actually details of the distribution. So in words, we want to compare details of the distribution. Let's give names to the two distributions. G0 is the distribution of the outcomes under standard of care. G1 is the distribution of outcomes under experimental therapy, under the new treatment. We want to compare the black G0 with the red G1. To proceed with such a comparison under a Bayesian paradigm, we need prior probability models on these two unknown distributions, G0 and G1. Or in other words, we need a probability model for G0, a probability model P of G0 and P of G1. We could now proceed with that probability model just using any customary parametric family. Like we could assume normal distributions, or since these are event times, you might want to use things like exponential distributions or gamma distributions or Weibull distributions. The problem in doing that, though, is if we were to assume a family for the G, like a parametric family, we would smooth over many of the detailed features that you see in the picture up there. Like assuming an exponential distribution would obviously miss a lot of the details that we see in the picture up there. Or in other words, restriction to a parametric family like a normal or something. In this case, you would probably use a normal after a log transformation, if at all. In any case, it would lose too many of the details. The alternative is to put a probability model on the infinite dimensional quantity of the random distribution. So in other words, to put the distribution on the distribution, and that is known as nonparametric Bayes. It's customary to abbreviate nonparametric Bayes as BNP. So from now on, I'll just abbreviate it as BNP, like Bayesian nonparametrics. The distinguishing feature to parametric inference is we have now infinite dimensional random quantities. So in a way, it's almost the wrong term, because rather than non-parametric, it's actually infinite parametric. Like we are putting probability models on infinite dimensional quantities. If we could put now a very flexible prior probability model on these two distributions, the red one and the black one, then in principle, we could update these prior probability models conditional on the data. Then we get posterior distributions for the unknown G0 and G1. And then we could formalize our relative preferences, like preferences of the type, it's more important to reduce T early on than later on. And under those preferences, we could compare the red and the black posterior distribution and let the better one win. That's the plan, yeah? In order to carry that out, though, the important thing is in order to carry that out, we need flexible probability models for the unknown distributions. We need flexible probability models that do not lose the detailed features that we see in the picture up there. And that is known as BNP. Let me just wrap that up, what we would do in that example then. We would start out with probability models for the unknown G0 and the unknown G1, probability models, flexible probability models for the red and the black distribution, flexible enough that they don't just smooth out the subtle differences. And then what we would essentially do is we would multiply the estimated probability models with elicited preferences. Do you see here that we have elicited relative preferences for improvements where the preference for an improvement at 0 is the highest, because if you can immediately go home, that is really that is highly preferred to even staying 1 or 2 days. So initially for early days, there's very high utility, and then later on it starts to flatten off. Like going home after 30 days is still better than going home after 40 days, but the difference is not so much. And then when we multiply our estimated distributions with those elicited preferences, then we get expected utilities, and the bigger one is the treatment that we want to recommend. I don't want to bother you with the details of setting up the decision problem, but can you see that an important part of the setting up the decision problem is we need these flexible probability models for G0 and G1. And that is where BMP comes in. That is where non-parametric Bayes comes in. So because, yes?
There is a question. Silvio, você pode ligar o microfone do Rodrigo Ferrari, por favor? Rodrigo Ferrari wants to ask a question to you.
Please, go ahead. Oh, I can see it here in chat. Is there an equivalent to confidence intervals for non-parametric Bayes?
Yeah, I was wondering, since you were talking about Bayes factors, if it was possible to use some sort of credible bands to compare these two distributions, right? To see how much they intersect, how much one seems to be, I don't know, larger than the other, so that I could make a decision that did not rely entirely on Bayes factor, or at least as an alternative.
Good comment. Can I answer it a little differently? Like the question is about, like Rodrigo is highlighting, that we want to quantify uncertainty of the estimated distributions, or in other words, the unknown distributions that are shown here. The point, like here in the picture, I only show point estimates of the unknown distributions, but it's really important in many problems that in addition to the point estimate, you have a quantification of uncertainties, which could be by credible intervals. Like credible intervals are the equivalent to confidence intervals under Bayesian inference. Typical thing to do would be to have like pointwise credible intervals. Like for each t, we could show like a little interval that with high posterior probability contains the unknown distribution at that point. On this figure, I did not include credible intervals. I did not include, I did not visualize the uncertainty. On the title slide, if you remember the title slide, the left figure, let me quickly flip back to it. On the title slide, at least in the left figure where I had just a univariate distribution, I tried to visualize uncertainty by showing in the gray shades. I showed like, I don't know, 50 or so random draws from the posterior. With these 50 or so random draws of the posterior, you could now build credible intervals, pointwise credible intervals. So quick answer, yes, we could add credible intervals. We could add credible, pointwise credible intervals for the unknown distributions. And yes, that is something very important for the inference, because if you have high uncertainty, you need to adjust for that in your final decision. Does that kind of answer your question? So
I guess so. So what you're saying is that it is possible for you to derive a credible interval if we think of the process maybe in a point-by-point scenario. Is that right? Like you sample from your curves depending on where your curve reaches for each point. You derive an interval for that point, and then joining them all, you end up with a credible interval. Is that so?
yes, perfect. Like
Right.
I'll try to do it here. Oops, doesn't seem to quite work. So each of these point estimates of the line, somehow it doesn't seem to work. I tried to add like a little shaded band around the point estimates to indicate credible intervals. And then we could try to work out rules of the type I think you're suggesting in your question. We could see if the credible intervals intersect or not, and only if they're well separated, then we say there's sufficient evidence that the two are different. Something like that we could do, yeah. But so it definitely makes sense to, in general, visualize the uncertainty. I'm having some problems here on my screen. I can't. I opened the chat box and I can't close it anymore. That is too funny. But no, it's okay. So importantly, we also have uncertainties about the unknown distributions, not just point estimates. But we are jumping ahead a little bit. Like I introduced the example just to motivate that we need probability models for the unknown distributions. And I showed you the pictures before I even talked about any notion of how to construct such probability models. So now we should talk a little bit about constructions of such probability models. And the first specific probability model for unknown distributions I want to briefly talk through is the one that's known as the Dirichlet process. It's by far the most widely used one, maybe too much used. The main reason for its wide use is computation turns out very simple. So we have to talk now about probability models for unknown distributions like the G0 and G1 in the previous example. And one of them is the Dirichlet process. It goes way back to an old paper in 1973 by Ferguson. We write G.E.P to indicate that the unknown distribution is generated from a Dirichlet process prior. Where the unknown distribution F, we could write it like this as a sum of atoms. Implicit in writing it like this, implicit in this, I'm already anticipating one important property of the Dirichlet process prior. It generates only discrete distributions. So it generates discrete distributions that can be written as a sum of point masses. Each of the delta MH, that's a point mass at an atom located at MH, and the size of the probability point mass is P sub H. So that's just some notation to represent the unknown distribution. At this moment, it's still a discrete distribution that is sometimes a little bit awkward, but at this moment we'll fix it soon. Yeah. And I promised you the Dirichlet process is a very easy and straightforward model. It's so easy that the definition fits on the next two lines. Yeah. So just proof that it's easy. It fits on the next two lines of my slide. It can't be easier than that. Here's the construction. We generate the atoms, the location of the atoms, the M sub H. We generate them by IID sampling from some fixed probability measure. So that fixes the atoms of the discrete distribution F. And the weights, now the weights we cannot generate by IID sampling because they have to add up to 1. Instead of IID sampling, here's the next simple thing we can do. We start out with IID beta random variables. We start out with random beta variables. And using those random beta variables, we can then define the probability weights P sub H. We define P sub H as VH times product of 1 minus VL for L less than H. What's simply going on here is think of the V sub H as fractions. Then V sub 1, like initially you're starting out with a total probability mass of 1 that we have to distribute to the different atoms. Then V sub 1 breaks off a probability mass V1 from the initial probability mass of 1. So V1 becomes P1. What's left is 1 minus V1. And then V2 takes a fraction V2 of the remaining 1 minus V1, and that becomes P2. What's left is then 1 minus V2 times 1 minus V1, and V3 breaks off a fraction of that remaining product 1 minus V2, 1 minus V1, and that becomes P3, etc., etc. The process is known as stick breaking. So this is just a construction to generate infinitely many weights that add up to 1. And it's as simple a construction as it could be just by taking better distributed random fractions of a total probability mass of 1. That's it. That's a full definition of the random probability measure. It's a slightly special one because it's a discrete one. And did you notice part of the construction is that the P sub H, at least in expectation they're actually ordered. Like the first one is always bigger than the second in expectation, etc. But now we have a construction for a random probability measure. In the construction, I used 2 parameters. I highlighted them in red up there. I had to state the probability model from which we generate the atoms. That was the F star, known as the Bayes measure. And I had to tell you the parameter of the beta distribution that we use to generate the fractions. That's the M, but that's all we needed. So in other words, the Dirichlet process prior on the random distribution F, it is indexed with the 2 hyperparameters M and F star. So it's easy to define with the 2 lines above. It's also easy to write down the hyperparameters. It's just a pair of M and F star. And actually it's not immediately obvious, but you can easily show that F star actually becomes the expectation of the random probability measure. So think of the Dirichlet process, the G.E.P, it's a machine that generates random probability measures. I think on the next slide, I'll actually show an example. Let's look at the example first. Yeah, here you see it. I'm representing the probability measures by way of the CDF because they're discrete distributions. If I show the probability function, it looks a bit funny. It's like all these little sticks. So instead of the probability function, I actually show the CDF. Then the dark black one, that's the F star. The dark black one is the F star. And the gray ones, those are possible realizations of the random probability measure. Can you see how they are centered around the F star? Or in other words, the F star actually becomes the expectation of the random F. And there was a second interpretation. Let me flip back to the previous slide. So the F star is interpreted as the expectation of the random probability measure. And excuse me. And the M that has an interpretation like a precision parameter. The M is also known as total mass parameter. It serves as a precision parameter in the following sense. If you take any event A, if you take any set A, then since the F is random, the F of A is random, right? It turns out the F of A follows a beta distribution with the indicated parameters. Can you see how the M enters here? The M does not affect the expectation of the beta distribution, but it just makes it more and more precise. Like if you generate a beta distribution with parameters, with 2 parameters, the larger the 2 parameters, the more peaked the distribution. So the M is something like a precision parameter. So a message to take away from this slide is it's our first construction of a prior probability model for an unknown distribution. it probably is not yet useful for the purpose of our previous example because it's discrete, but really in a moment we'll fix that. The main features of that probability model for the unknown f is it's very easy because it only took me 2 lines to define it. It's indexed with 2 hyperparameters, the base measure f star and the total mass m. They have easy interpretations. It doesn't get much easier than that. That's one of the reasons why the Dirichlet process is so popular. But one of the important things to wrap your head around is just the notion that the probability measure itself can be the random quantity. So the Dirichlet process, the BMP prior, puts a probability distribution on a probability distribution. It's a model for a random f. So here the left figure that I already showed you before, that shows prior simulation from the Dirichlet process prior. And another important feature of the Dirichlet process model is posterior updating is actually amazingly simple. In a moment, I'll tell you how to do that exactly. Here you can see just a picture of posterior updating. What we have here is we have data xi that are observed under the unknown f. That data is shown as the little pins here on the horizontal axis. And conditional on that observed data, we update our probability model on the unknown f. And this figure shows, summarizes the posterior distribution. Can you see what happened? Like around 2 is the data. And the posterior distribution has, as desired, the posterior distribution has shifted the probability model towards the right. So now it is centered around 2 instead of earlier. If you look on the left side, it was centered around 0, right? So it is properly done, that shifting. Here in the title, you have already a quick summary of posterior inference under the Dirichlet process when you have independent sampling from the F. The first important thing to see is, can you see that the posterior distribution for the F given the observed data? It's again a Dirichlet process. So in other words, the Dirichlet process prior is a conjugate prior under independent sampling from a random distribution. So if you have the standard density estimation problem, we have IID sampling from F. Then the Dirichlet process is a conjugate prior because the posterior is again a Dirichlet process. And I can briefly tell you the nature of that updating because it's so simple. The total mass parameter just gets incremented by the sample size. So M1 is the original M plus, say, little n, the sample size. In our case, I generated here something like 10 points. And the F1 star, the updated base measure, is a linear combination of the original F star plus the empirical distribution on the data. So the base measure updates as a linear combination of the original base measure from the prior plus the empirical. And the total mass parameter just gets incremented by the sample size. So it's really relatively easy. So the main limitation of the Dirichlet process model itself is, I hope I convinced you it's really easy. Yeah? The main limitation of the Dirichlet process model is the discrete nature of the F. We immediately saw it when I wrote down the notation for the F. If I can write the F as a sum of atoms, then it's obviously a discrete probability measure. And that is awkward for many applications. When you do density estimation, you want to show a smooth continuous distribution, right? The fix though is easy. Here's what we'll simply do is, we'll use again the F, we start with a Dirichlet process prior, but rather than using the random F from the Dirichlet process prior for our unknown distribution, I just add a convolution with the normal kernels. So think of the F as a sum of point masses, like it simply pins on the real line. All what we are doing, we are convoluting those pins on the real line with no Gaussian kernels. Then you get, in the end, you get a mixture of Gaussians. Like an integral with respect to a discrete integrating measure is a complicated way of writing a summation. What happens in the end is we're just replacing the earlier point masses at the m sub h. We are replacing the delta sub m sub h that we had on the previous slide. We are replacing those by Gaussian kernels. So we're moving from a discrete distribution to a mixture of normals, which is a very flexible model. Looks nice. It gives us smooth densities. A very nice review of Dirichlet process and Dirichlet process mixtures appears in a paper by Ghoshal 2010. A quick application, like second little example. Let's assume we have data. The data could be, for example, gene expression for some gene of interest. So y sub I is gene expression for n equal 50 samples. So we have 50 samples, y1 through y50, from an unknown distribution G. And we want to put the prior probability model on the distribution G. Here's what we do. Our flexible prior probability model on the G, we're using a Dirichlet process mixture. Again, for the same reasons as before, you don't want to proceed with a parametric model because that might impose too many restrictions. Like if we were to assume, if we were to restrict the G to being a normal distribution, we could not get multimodality. If we were to assume it a bipolar or not, still it would be restricted. Dirichlet process mixture is now a BMP prior for the unknown G. You can essentially think of it as a mixture of normal model, but it's a mixture of normal model with well-specified prior and everything. Excuse me. Just following up on the example, on the left side, I'm showing a histogram of the data. So this is a histogram of 50 observations by 1 through by 50. And the right side shows now the posterior inference. The posterior inference is again a mixture of normals. And I show in the thick gray line, that is the posterior mean. The many thin lines, the many spaghetti around the gray line, they show many posterior draws. And if you focus now on any one point, using those posterior draws, you could create credible intervals. So that's back to Rodrigo's comment. We could create pointwise credible intervals to show our uncertainty. And by comparison, in the dashed yellow line, I'm just showing a kernel density estimate. So a typical thing to notice here is if you just want the point estimate for the unknown distribution, you probably don't need a BMP model. Just for a point estimate, just use a kernel density estimate or whatever is your favorite method, and you're probably doing just as fine. The really important thing of the BMP model is that in addition to the point estimate, we get an entire posterior distribution for the unknown guy. And that allows us things like credible intervals. Understanding this uncertainty is important when you want to carry out comparisons, because without uncertainty, we would just have 2 point estimates and we don't know how significant is the difference, right? So that's all I wanted to tell you about this example. But back now to the Dirichlet process mixture. So the Dirichlet process mixture that we introduced now 2 slides ago, it is a BMP version of typically a mixture of normals. Obviously, it need not be a mixture of normals. It could be a mixture of many other distributions. For the purposes of understanding it, and especially for computational purposes, it's very useful to replace the mixture model by a hierarchical model. So here's the mixture model again. Not sure why I didn't spell it out. So this is the mixture model from 2 slides ago. Let me just flip back to look at that again. Flipping back, where is it? It's this mixture model. The G is a mixture with respect to the Dirichlet process prior on a mixing measure of Gaussian kernels. So going back here, this is the mixture. We have the data Y is a sample from an unknown G, which is represented as a mixture of normal kernels. The dot 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 here stands for the normal kernels. And we are mixing with respect to a random Dirichlet process measure f of theta. It is computationally convenient to where that integral, since the f is discrete, that integral is just a complicated way of writing a sum. So this is really just a sum over infinitely many Gaussian kernels. Each of them weighted with the p sub h and centered at the m sub h. Whenever you see a mixture model, you can replace it by a hierarchical model by introducing latent quantities. We call them here the theta I. So I introduced for each observation, I introduced the red theta I, and writing that theta I is generated from f, and then yi given theta I is just generated from the kernel, that is the dot 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 up there, is a totally equivalent way of writing the mixture, because when we multiply the two lines, we're getting the normal kernel times the random f. And when we integrate out the latent red theta I, then we are exactly back to the line above. So these two lines of the hierarchical model are identical to the mixture that's written on the top. The advantage of writing it like this is that we have now, we can now work with these latent theta I's. And there's one funny thing happening that is actually very important and used in many applications. Remember that f, we wrote that f as a sum of point masses, right? That f is a discrete probability measure. When we are taking a sample from a discrete probability measure, then with positive probability, we'll see many ties. Many of the theta I's will be identical. Or in other words, when we are taking a sample of size 50, we might only have a much smaller, maybe cap k equal 10 number of unique values of the theta I's. Let's give names to those unique values. Let's call them theta star. Then let me just quickly see what's where I'm heading here. Then for the purposes of talking about computing, it's convenient to introduce indicators. Let's call them set I, where those indicators just they just match the unique values with the actual theta I's. So we are saying set I is equal to j if the theta I is actually tied with the jth unique value. So instead of introducing the red theta I's, I could just as well introduce the theta stars and the set, and that would be equivalent. Sorry, can I still go back? Careful, this is not just a footnote. That's actually a very important feature. Like what seems at the moment just like a footnote and a nice observation about the Dirichlet process mixture. It's actually very important because it gives rise to a notion of clustering the data. What we could do now is we could arrange our data yi. We could arrange it in clusters by grouping them with respect to the unique values, like all the data points, all the samples that are linked with theta I's that are tied with unique value theta 1 star, we called it group 1. All the data that are linked with theta 2 star, we called it cluster 2, etc. So on the fly here, inference under the Dirichlet process mixture defines clustering, defines a random partition. Many of you might be familiar with using mixture models to define partitions. That's exactly what's going on here. We are using the mixture model, but now the mixture model with respect to the Dirichlet process random measure to generate a partition of the data, to introduce a notion of clustering. So this is what I just said. We can use the unique theta stars to introduce a notion of clusters, where the chief cluster is just a set of all observations whose theta I, whose latent parameter theta I is tied with the chief unique one. And alternatively, we can represent it with those, instead of using the theta i's, we can just represent the clustering with these indicators. Remember, set I is equal to J if the ith guy is tied with the chief unique value. So as a side product of inference under Dirichlet process mixture, we are introducing here a probability model for a random partition. Because the theta i's are random, that makes the set i's, the indicators, random. Or in other words, the clustering is random. So we have now a probability model on a random partition, on a random arrangement in clusters. And there's something important happening. That's why I started to introduce that. Conditional on the F, like if we condition on the F, the joint distribution of the thetas is simply the random sample from the F. Can I flip back to the previous slide? If we flip back to the previous slide, can you see, given the F, the theta I are just IID from the F. That comes from the representing the mixture model as the hierarchical model. So given the F, the theta i's are just an IID sample of the F. In other words, given the F, the joint distribution of the thetas would just be product I equal 1 to n of F of theta I. But when we marginalize the F, then we get a marginal joint distribution of the thetas. And we can always write that marginal distribution of the vector theta. We can always write it as P of theta 1 times increasing conditionals, that you can always do. But in general, it could be something, this might be something analytically intractable. It's not obvious that these distributions are available, but this is exactly where we luck out. We run into some good luck here now. It turns out these distributions here in the marginal, these conditional distributions of the marginal because we are removing the unknown F. The conditionals under the marginal, they turn out to be of really easy form, and they're so easy and so important that they get a special name. We call them the Polya urn. Before I write down the Polya urn, can I just point out the conditional of theta I given theta 1 through theta I minus 1, we can also represent it in terms of those indicators, set I, because if I just tell you which of the earlier guys that the new guy is tied with, that essentially tells you that complete conditional. So spelling out the Polya urn, we might just do it now for the set I's. Yeah? Sorry, we're not going, like, this is all I wanted to tell you for the moment about the marginal distribution of the thetas and the notion that we introduce clusters. So the important message from this slide now is posterior inference under the Dirichlet process mixture actually implies inference on a random partition of the data. It seems just a side product, but it's actually one of the main reasons why we use Dirichlet process mixtures in many applications. So that's all I wanted to tell you for the moment about the Dirichlet process model and the Dirichlet process mixture. Main question, did you get the idea? It's actually a very simple model. Yeah, it was so simple I could specify it in 2 lines on the slide a few slides ago. Posterior inference is easy. I didn't talk you through all the details, but I tried to convince you it's easy. In particular, it's conjugate and IID sampling. When we change the Dirichlet process, which is discrete, to the continuous Dirichlet process mixture, then we essentially just have a mixture model. That mixture model gives rise to random partitions, which we can use for inference and clustering. So that's what I talked you through with the Dirichlet process model. Before we move on, I want to talk briefly about another totally alternative model. So we are changing gears now. We have talked enough about the Dirichlet process. I want to talk about another prior for random distributions. Priors for random distributions are known as BMP. And here it is. Our second, so this is becoming our second BMP model now. It's the Polya tree. It's known as the Polya tree. In plain words, the Polya tree is simply specifying a random histogram. That's all what's going to happen. When you try to construct a random histogram, how would you do it? Here's one way of doing it. We can start with, let's assume for simplicity, let's assume that we want to have a random histogram on the unit interval from 0 to 1. Then let's start with a random histogram, just splitting into 2 bins. 2 bins is a bit little, so we might want to refine it and split each of the bins again into 2 bins. So now we have a histogram of 4 bins. That becomes a little finer, but it is still a bit very coarse. Again, we can split each of these bins again into 2 bins. So now we have a random histogram with 4 bins, and we could keep on going like that. That's exactly the construction of the Polya tree. Or in other words, the Polya tree creates a random histogram by setting up random splitting probabilities. So when we go from the first to the second case, we have to take the random, like these 2 random bins, we just use a better distribution. We'll use a better distribution for the first 2 random bins. Then splitting each of the first bins, we'll use again a better distribution for the conditional splitting probabilities. Then we'll again use a better distribution to split each of the already finer intervals now. And we'll keep on going like that. If we keep on going like that forever, we create a random distribution. That's the whole idea. The bins will denote in general as B0, B1 is the first 2 bins. B00 through B11 are the next 4 bins. B000 through B111 are the, now we are down to 8 bins, etc. So all what I owe you now is the probability models to create the random histogram under these bins. And I already gave it away in the last sentence by telling you it's better distributions. Here's then a formal definition of the Polya tree. And again, it's very easy. It actually fits on 2 or 3 lines. It's almost even easier than the Dirichlet process, which is amazing. So a Polya tree prior is a prior probability model for an unknown distribution. And here's how it proceeds. We are defining can you read, this is the splitting probability. B sub epsilon 0 given B sub epsilon. Remember, I indexed my partitioning subsets with binary sequences. So if we split B sub epsilon, for example, if we split B00 into B000, then we need the conditional splitting probability f of B000 given B00. And we generate that conditional splitting probability from a better distribution. These better distributions generate independently across all bins. We generate these splitting probabilities. And it's actually all I have to tell you to define the random histogram. Just want to highlight, in that construction, we needed 2 hyperparameters, or in other words, the Polya tree model is indexed with 2 hyperparameters. We need the parameters of these better distributions that we use for the splits. And we need to specify the nested sequence of partitioning subsets. On the previous slide, I simply used binary splits always into halves, but it need not be always into halves. Actually, in choosing these hyperparameters, we can conveniently specify the prior expectation. Like fixing these hyperparameters, we fix the prior expectation. Here's one thing we could do. There's 2 alternatives. The 2 alternatives is either if we choose we can either choose the partitioning subsets as dyadic quantile sets under the desired centering distribution. Dyadic quantiles are simply the median, the quartiles, the octants, etc., octiles, etc. Or we use arbitrary partitioning subsets and choose the parameters for the better splitting distributions as the conditionals under the desired base measure, under the desired centering measure F star. That's actually all that needs to be said. I went through that a bit fast in the interest of time, but main message you should get is the Polio tree is easy to specify, and it is easy to center it. It's easy to specify it such that it's centered at some desired centering distribution. Just see my notes where I'm headed now. One big difference between the Polio tree and the Dirichlet process is it's actually possible to specify the Polio tree such that we create continuous distributions. That is controlled by the choice of the alphas. I don't want to go into much detail there, but by appropriate choice of the alphas, you can actually make sure that we get a continuous distribution. And here's another fun fact. It turns out that the Dirichlet process actually is a special case of the Polio tree. The Dirichlet process arises from the Polio tree when we choose our sequence of those alpha parameters. The alpha parameters are the parameters that index the beta distributions for the random splitting probabilities. If we put a restriction on how these alpha parameters are chosen, then we get the Dirichlet process back. So that's an alternative definition of the Dirichlet process. Just nice to see that. There's something a little awkward about the Polio tree. It can generate discrete distributions, but the random distributions will always show the densities will always show discontinuities at the change points between the histogram bins, and that is sometimes awkward. So there are some papers that try to remove that by taking a mixture of Polio trees. For the moment, that's all I wanted to tell you about the Polio tree. So now we have already had, let's keep track, we have already had two BMP models already, the Dirichlet process and the Polio tree. Both of them were fairly simple. I hope I convinced you of that. For the Polio tree, all I had to tell you for the Polio tree construction to define a Polio tree prior for a random F. Really, all what I had to tell you was that the conditional splitting probabilities are generated from a beta distribution. So it's really a one-liner. It's amazing, but it's even easier than the Dirichlet process prior. One limitation of the Polio tree model is the construction that I talked you through that is very natural for a univariate distribution. For bivariate distributions, you can still think of histograms, but now it becomes bivariate histograms. Starts to become awkward, right? In higher dimensions, it quickly becomes awkward. Practically, the Polio tree prior is most useful for univariate distributions, but it's a bit awkward for higher dimensions. That's one of the limitations. So I want to still talk about yet another big class of BMP priors, known as normalized random measures. Excuse me 1 second. It's a large family of BMP models, so it's even more BMP models now. All of them are discrete, so I can write it always as sum of atoms. I've changed notation now just to indicate it's a different model, but of course, could use any names here. In this notation, I denote the point masses, the atoms, as mu sub h, and the weights as eta sub h. So it's like Greek E eta sub h. So normalized random measures create again discrete distributions. We already know the discrete nature of the random distribution is not going to be a major problem, because if we desire continuous distributions, like for density estimation, simply add a convolution, say with Gaussian kernels, and you get continuous distributions. Main thing is, here's how we're going to construct it, and in a moment I'll briefly talk you through the construction. It's going to be quite simple. We'll actually generate these weights. First, we'll generate unnormalized weights. Let's call them eta tilde. So they will not yet be normalized to sum to 1. Then we simply divide by the sum, hoping that the construction is such that sum converges. And that's how we generate it. So what I owe you now is I owe you a comment of where the mu's come from and where the unnormalized weights are. I just wanted to highlight the weight up here. So I owe you an explanation where the highlighted atoms and weights come from. And that explanation is actually easiest in terms of a picture. Can you see in the picture down there? I indicate on the picture is stolen from Favaro and T, 2013 paper in Stat Science. In that picture, I'm showing a Poisson process where one axis here is the desired sample space where the atoms are located, the mu's are located. The other axis is where the eta tildes are located, the unnormalized weights. What we are doing then is we are generating pairs of atoms and unnormalized weights from a Poisson process with an inhomogeneous Poisson process from X cross R plus. X is the desired sample space for the atoms, and R plus is where the unnormalized weights come from. Using intensity nu, the Poisson intensity is that colorful surface here. And if we generate pairs with that Poisson intensity, then we get random points. I should have indicated them in the figure. I couldn't because I stole the figure. But there could be one here. Can I mark that up? There could be one. Like, can you imagine how there's like random points, like the Poisson process? It's a point process, creates like random points in there in that plane. Each of these points defines a random mu sub h and unnormalized weight. If we use the atoms and unnormalized weights to create a random distribution, we get the random f. This is indicated here on the x-axis with the pins. That's it. That's the construction of a normalized random measure. The attractive feature of that construction is that by choosing different intensities, we get a huge variety of BMP models. And not surprisingly, again, the Dirichlet process is a special case of it. But before we get there, let me just talk you through some of the popular classes of such models. So here's just some references. So first of all, it generates a discrete distribution, as we saw in the previous cartoon. But again, we're going to include a convolution with an additional kernel, like a Gaussian kernel, to create continuous mixtures. That way we create continuous distributions. Posterior inference under these models is still relatively easy. It's relatively easy posterior updating. Discussions of posterior updating in such mixtures with respect to normalized random measures appear in these references. That's Barrios, Nieto, and others in Stat Science. In the same Stat Science volume is a paper by Favaro and G.E.P. The nice discussion is also in Argento and others in computational statistics and data analysis. I forget the year, maybe it was 2014 or so, a while ago by now. But all of these papers, they discuss posterior updating in a very special case. Remember on the previous slide, the normalized random measure was characterized by the Poisson density. We need the intensity of the inhomogeneous Poisson process. We usually assume that these factors into a function of the unnormalized weight and a function of the atom, or the location of the atom. The H naught, that will define the centering of the random probability measure. And if you choose for the rho an expression like this, let's not go into details here, that defines the class of known as normalized generalized gamma. It's just one class of BMP models. But in particular, and that's one of the reasons why I mentioned it here, again, we get our friend the Dirichlet process. Oops. We get the Dirichlet process as a special case of the normalized random measure. You get it when there is a kappa appearing, and if you set the gamma equal to 0. So if you choose kappa equal 1 and if the gamma is 0, then the expression simplifies for the Poisson intensity, and that happens to again define the Dirichlet process. So it's funny how we keep on coming back to the Dirichlet process. It has been said that the Dirichlet process is to BMP a little bit what the normal distribution is to parametric inference. Like it pops out as a special case in many other areas. It's very central to BMP. That's all I wanted to tell you about normalized random measures. So to recap, we had now 3 BMP models already. We had the Dirichlet process, we had the Polio tree, and we had the normalized random measures. I didn't talk about through deep details on each of them, but they are not terribly difficult. I hope I convinced you these BMP models are not really difficult constructions. I wanted to briefly show you still an application, that's the application that showed up on the title slide. Here's the application. We have data on triples of counts. For each of couple thousand actually tripeptide tissue pairs. So these are pairs of tripeptides and tissues. What the investigators really want to find out is they want to find out which tripeptides preferentially bind to which kind of tissue, because then it could be used to devise cancer treatments. That's the intention. But for us, for the statistical modeling issue, all what we need to know is we have triples of counts, and we want to find those observations I where these counts increase rapidly. Here on the left side, you see the data. Each of the lines corresponds to 3 counts. They're just connected, yeah? Can you see that most of them, in most cases, the 3 counts are kind of comparable, and only some of these lines, they rise sharply. I marked them here in red. So some of these lines rise sharply. Those are the ones we want to find, because that means those are the tripeptides that preferentially bind to certain tissues. That's the interpretation. So the inference problem is we want to identify these red lines that significantly rise across the 3 counts. To talk about that, we need a sampling model, a very simple sampling model. We just assume independent Poisson distributions for the 3 counts. So the 3 counts are indicated here at the 3 vertices of each of these lines. And if we index the 3 Poissons with mu I beta, and mu I delta, then identifying increasing lines, the red lines simply correspond to the red inequality. Can you see when the beta is greater than 1, that means the mean for the second Poisson is larger than the mean for the first Poisson. And if the delta is greater than beta, then it means that the third count is again bigger than the second count. So 1 less than beta less than delta means you have a red line that keeps on going up. So we are after finding experimental units that satisfy the red inequality. And here's how we proceed. Like here's the sampling model that defines the top level likelihood. We have to now define a random effects distribution for the mu I, beta I, delta I. The random effects distribution that we use is we use a Dirichlet process mixture. Using a Dirichlet process mixture. Remember again the inequality. Like try to remember that inequality, that's the critical one. We want to find these guys. Beta greater 1, less than delta. Here we have on the x-axis is the beta. This is the beta. And on the vertical axis is the delta. Sorry, the font has become very small. So beta greater 1, less than delta. I think it's this quadrant here, right? I goofed. Can I still? This is the quadrant we're after, right? Are these the red ones? Because now delta greater, beta greater 1. These are the ones we want to find. And we use the Dirichlet process mixture for the underlying random effects distribution. Can you see how that's important that we didn't just use a normal, yeah? And then like here are the winners, like all these guys are winners. All these guys are tripeptide tissue pairs that are interesting. That's the application. And it actually brings us to the end of the first part. At this moment, you should have some idea of these free BMP models. I hope I gave you some flavor of interesting applications. And maybe this is a good moment to take a break if there are questions. Any questions, comments? Otherwise, can we just take like a 2-minute break just to take a breath? And then we move on to the second part, talking about regression. So far we talked essentially about density estimation. I think of density estimation it's like the easiest statistical inference problem. You have an IID sample from an unknown density, try to find the density. That's what we are doing here, right? So if there are no, if there's any comments or questions, just put it into chat or just speak up.
No comments, people?
How was the pace? Like, were we too slow or too fast? Or okay?
No, it's okay. I guess it's okay. Yeah.
Oh, sorry. I just noticed my speaker died. See, I'm using a.
The sound is really good. Yeah.
Oh, now you're back. I didn't hear you before. So hope it was an okay pace. And you were very quiet out there. Nobody said anything for an hour.
Yeah, nobody has any questions?
It's very early for me here, but for you, it's already going towards lunch.
Yeah. Rodrigo, there is no question. Rodrigo, that make you a question, works with Polya tree.
Oh, so 1 second. I'm still having problems here. It's embarrassing, but
Do you have problems? During the presentation, we had some gray box in the slide, but you removed that.
Oh, the gray box happened when I tried to when I marked something. Is the gray box gone now?
No, now it's not appearing anymore. You just remove you.
Probably happened when I tried to mark something.
Yeah. Now we have that.
Oh, so it happens when I try to fudge something. I'm still trying to. Can I just take a 1 minute break? Trying to fix my.
Yes, we can have a break of 1 minute.
And then we are back with part 2. So just give me 1 minute to try to fix it and stop sharing, and then I'll start again.
Okay.
And I need power on my laptop. I shut it.
Okay.
Just had to put power on the laptop because I shut it because there was some noise in between.
I think I have everything set.
Now we have a noise. No, not anymore.
Done?
Okay. No, we have a very noise in the end.
Is it there still or?
Yes. No, not anymore now.
Okay. Scream if it becomes too irritating. Like in between, I took the power off the laptop, assuming that the noise came from the fan from the laptop. It sometimes happens. Just,
no, it's okay. You don't have the noise anymore. Now we have the noise.
It's back.
Yeah, it's back.
So sorry. I don't know what to do now. Oh, it might be the cable here.
Not anymore. Disappeared again.
No. I think I have an idea what's happening. There's a bad cable. Give me 1 minute. I'll try to replace it.
Yes.
If I find another one. Like many of us have way too many little cables, and when you look for the right one, of course, you don't find it.
Now you don't have the noise again. I think it's just a cable that is not.
No, it is a loose. It is a bad cable. That's what's happening. Yeah? Excuse me, 1 minute. I'll run to another room looking for a cable. If I find it, I'll fix it. If not, we'll have to improvise. 1 second, yeah.
Okay. But it's not too bad. If you couldn't find it, it's not a problem. Seu som também tá ruim, Michel. Tá ruim seu som.
Different cable. Is it any better now? Is the noise gone?
Yes.
Oh, perfect. So then it's time to, that was perfect because that gave us a little bit of a break to catch our breath for everyone.
I guess we don't have any questions here.
That's common, yeah. Whenever you teach us something. So then let's continue with the second part. Here's up and ready for it. So after talking through density estimation, in my mind, the natural next thing to talk about is regression. And so let's talk about BMP for regression. Talking about BMP, non-parametric Bayes for regression. Here's what we have in mind. Here's a regression of survival times. For event times, it's for event time data, it's often customary to plot instead of CDFs to replot survival function, just the complement 1 minus CDF. So each of these lines is the survival function 1 minus CDF for, I think it's something like 8 different combinations of covariates. Call the covariates, call them X. Then the figure shows a family of probability models, F, indexed by X, right? Each of these lines is one F sub X. For X equal, like the dark black line is a small tumor size, high dose, and ER positive. There's like 3 baseline covariates and 8 different combinations of these, a good number of combinations of these baseline covariates. And for each combination, I show a different distribution. Each of these lines is a different survival function, 1 minus CDF. So we are now what's happening is instead of having just one density, instead of having just one unknown distribution, now we have 8 unknown distributions. Like the F is indexed by X. That's what we want to do. Or in other words, I really think I think of regression in general as regression is about families of distributions, G sub X. Like in the previous picture, there would have been 8 different distributions, G1 through G8. And I want to briefly talk you through one popular probability model, one popular BMP model for such families. So now we need a prior for the entire family, not just for one guy. Perhaps the most popular one that people build entire careers on is the dependent Dirichlet process, the DDP. So I want to talk about that a bit. Before, like in a moment, I'll specify the model. It will be amazingly easy. So just to celebrate it a little bit, I want to briefly talk you again through the setup. So I said it already in words, just want to spell it out. The assumption is, like in any regression, we assume that yi given x comes from f sub x. If that f sub x, if that were just now a normal linear model, then we are back to a parametric normal linear regression. But in general, we could go non-parametric on this. We could go non-parametric on it, maybe just by changing the mean function in a normal, like if that f sub x here were just a normal linear model, then we're back to parametric inference. If you replace the linear mean function by a general function, that's one way of going non-parametric on it. And people have done it before. Alternatively, we can go non-parametric on the residual. Like we could have a linear mean function and just go non-parametric on the residual. Going non-parametric on the residual kind of reduces it to density estimation again, because then all what we say is that epsilon I, the residual, comes from some distribution, and we need a prior on the distribution. Tim Hansen and Wes Johnson did it a while ago using Polio trees, for example. That would be a classic application of Polio trees. So then the f sub theta might still be parametric, yeah. Alternatively, we could use Gaussian residuals maybe, and go non-parametric on the mean function. Going non-parametric on the mean function, now we need a BMP prior for the mean function, say f in general. Popular choices to do that are, many of you might know Gaussian process models, so we could put the Gaussian process prior. That's one big, one widely used BMP prior. Alternatively, we could create a random f by using any kind of basis expansion, like writing a function with respect to some basis. The problem of putting a probability model on the function reduces to putting a probability model on the coefficients. And one of the popular bases came up already before. One of the popular bases is, for example, the Dirichlet basis, for a variety of reasons. That's very flexible. So at this moment, we just have to put the prior probability model on the wavelet coefficients, and there are many ways of doing that, etc., etc. A lot of that is done, and it's a big area. But I really want to talk about the third way of doing non-parametric. Did you get the flavor of what I tried to do here? First, I mean non-parametric, considering going non-parametric on the residual, or we go non-parametric on the mean function, or another third option is you go non-parametric on both. Then we are back to just the most general case, which I already had on the previous slide. Now we are saying that y comes from f sub x, where f sub x is just a family of random probability measures, and proceeding with Bayesian inference now, we need a probability model for that script f, that family of random probability measures. So we are mainly going to talk now, we're going to focus now on this case. The other cases are super nice and super important too. The first one just reduces it again to density estimation. The second one, we need a prior on the unknown function. That's a whole different ballgame. And the third one is now the most general one. But in the moment, we'll also reduce it to very similar constructions again. In particular, I want to talk you through one model. We're going to talk through the G.E.P model, the dependent Dirichlet process. Before talking you through the construction, just to motivate it, here's an application. It's actually the application, I think, that gave rise to the picture on the title slide. We have a large number of patients, n equals 700 women in a breast cancer study. Each woman comes with, each patient, we are recording in particular 3 covariates. Dose, which we just code as an indicator for high versus low dose. ER receptor, which we code as an indicator for ER positive or not. So it's a second binary one. Tumor size, that's like the size of the tumor, that's a continuous covariate. And we allow for an interaction of high dose and ER positive. We don't really need, I don't know why we have that last covariate here, it's not really needed. But with these 3 covariates, we have now a model for each woman. We have some observation. Observation, it could be time to progression or overall survival. And we assume that the data, the event times come from some probability model. But now it's not just one probability model for everyone, but depending on the covariate for every woman, you use a different distribution of event times. And for example, putting a BMP prior on that family of G sub x and updating it conditional on the data, we might get inference like this, which is exactly what we had on the title slide. So this is just by way of motivation. So in this case, we have like 8 different distributions. Each of these corresponds to a G sub x. So each of these corresponds to a G sub x, and we want to proceed with posterior inference on these 8 different G sub x. We do that using a DDP prior. So I should talk you through the DDP prior, and it's going to be very simple. It's not going to be difficult. This goes back to the paper all the way down to 1999, Steve McEachern. And it really started a huge cottage industry, like huge literature. It's the most commonly used model now for non-parametric regression in Bayesian inference. So what's coming up is a prior probability model, a BMP model for a family of random distributions. So really all what has changed from part 1. Earlier we had only one unknown G. Now we have a whole family. So we need a probability model for that family of random distributions. Did I convince you to think about regression as inference for a family of probability measures. That family of probability measures under parametric inference is simply described by different linear models. So with a finite number of parameters. For BMP, there's no such restriction. We simply have a family of random probability measures. I have to make so much blah blah because the actual construction is totally simple. Yeah, coming up now, it fits on a few lines. Let's first spell out the random probability measure for, like in the previous picture, we had 8 of them. Let's first spell out the first one for the first combination of covariates. We have G sub x1, and I again write the G sub x1 like before. Can you see on the right hand side? I have a sum of point masses, like the P sub h are the weights, and the atoms are M sub h. On the atoms now, I added a second sub-index for the x, yeah? So it's really an M sub x1, M sub x2, M sub x3. But it's again just a sum of atoms like before. For the second covariate, like think of that as 2 of the 8 random distributions that I showed on the previous slide for the replication. For the second covariate combination, again, we have a G sub x2, and again, it's a sum of point masses. I use now different point masses, M sub 2h, M sub 2,1, M sub 2,2, M sub 2,3, and so on. So I could keep on going here for all possible covariates. For each possible covariate combination, I have a different G sub x. And here's what I want now. I want the prior probability model for that family of G sub x. I want to construct it such that marginally for each G sub x, I get a Dirichlet process back, but I want to allow dependence. To get a Dirichlet process for each of them, what we need is, remember the first definition of the G.E.P that we had. The definition was that the atoms had to be IID samples. So they have to be IID samples from a base measure as we go down the atoms. Going down the atoms means going down the line, right? And the weights, they come from the stick breaking. Did I tell you that it's called stick breaking, the construction with the independent beta fractions? So remember, we wrote the P sub h as V sub h times product 1 minus V sub L for L less than VH, and the V sub h were IID beta. So we use that construction to create the first G sub x. And same construction to get the second one, the third one, and so on. The important thing is, for each of them to be a Dirichlet process, we need independence of the atoms in the line, right? But in the column, nobody stops us from making them all dependent. So we need to make all the green point masses dependent across X. We need to make all the blue ones dependent across X, and all the red ones dependent across X. Means we introduce dependence in the X, in the columns. Keeping independence, yes?
Could I say here that I will have an infinite mixture of regression models or no? In the sense, if you consider that the atoms are the regression coefficients, each observation could be their own regression coefficients. Could be this or no?
Quick answer could be, yes, it could be. Longer answer, you already use the construction that we'll actually have in a slide. But in a vanilla application, G sub 1 would just be the, let me go back to the picture. This might be G sub 1, the pink one. The pink one might be G sub 1. The red one might be G sub 2, etc. So there's no notion of an additional regression coefficient or anything. G sub 1 is defined as the sum of the point masses in the first line. G sub 2 is the sum of the point masses in the second line. But there's a.
But in the end, you will have just one regression model or just one line representing everybody, or you can take many regressions to represent groups of observations.
Quick answer 1. There is one unknown distribution G sub x, that's used for all patients with covariates with particular
Okay.
At the moment, all patients with the same X have the same distribution. There was one critical cheat that I made. Did everybody realize there's a disconnect between this picture and the construction? In the picture, my distributions are beautiful continuous CDFs. Sorry, it's 1 minus CDF, the survival function. Here they are beautifully continuous. Like, let's say this one could be the, let's see if I can write on this. This could be the G2. And the pink one might be the G1. Sorry, I'm gonna. One second, I'm having a problem here with my PDF preview. It seems something seems frozen. So each of the lines is a different G.
Okay.
My PDF preview is frozen. I can't. Oh no. It seems back to life. Sorry, it was frozen for a moment. Don't know what happened. So each of these lines is a different G, but there's a disconnect between the picture and the construction. In the picture, those were beautifully continuous CDFs. In the construction, they are discrete because they're sum of point masses.
Okay.
So we really did in the picture, these point masses were still convoluted with an additional Gaussian kernel. But to pointedly answer Diana's comment, all patients with the same X, they have only one G sub X.
Okay.
But the construction that you hinted at is coming up in a moment, yeah? At the moment, there's one distribution from which we generate the survival time for every patient with covariates X1. A second distribution from which we generate the survival time for every patient with covariates X2, etc.
Okay.
But so at this moment, it's still, at this moment, what I have on the screen, I have 3 discrete distributions. Those 3 discrete distributions are essentially free of the lines in the, like free of the survival functions in the previous slide. The only difference being in the previous slide, they were continuous because I used an additional Gaussian kernel.
Okay, thanks.
Thank you. No, thanks for your comment. Yeah, thanks for coming up. But so it is, here's the main idea. I said it in words. We are introducing dependence across the columns. So in other words, we are generating the atoms across the columns dependent, and it could be, for example, the dependence could not be a Gaussian process indexed with X. If the X is just categorical, then we can put in, then we can do anything else. One way of introducing dependence among numbers that are indexed with categorical X's. In my mind, the easiest way of introducing dependence is using ANOVA. So we could use an ANOVA for the green atoms, a different realization of the same ANOVA model for the blue atoms, etc. That introduces dependence for the random probability measures because we have made the atoms dependent in the columns, but maintaining the fact that the marginals are Dirichlet process priors. And the important thing about this construction, this is not obvious, yeah, but the important thing is posterior inference still remains as easy as before. And now I have already talking about mixtures, so I'm already implying that we use additional kernels. That doesn't really complicate inference. And this is just another example, but I would still like to move on to a construction that Diana already hinted at, which is the ANOVA DDP. All what that is now about is I'm going to talk you through a very special way of introducing the dependence on all the green ones, the dependence on all the blue ones, etc. And quick summary, what we are simply going to do is to introduce the dependence across the atoms. We are going to use an ANOVA model when you have categorical covariance. So here you can again see, can you see the M sub XH? Do you remember that was my notation for the atoms on the previous slide? For example, if you just have two covariates, like it might be an indicator for high versus low dose, and an indicator for ER positive or not, that would then create, with two binary covariates, we are really only creating 4 different distributions. So as Diane pointed out, in that case, we would just have 4 different distributions, and all women with covariates 0, 1. We assume that overall survival for those patients are generated from G sub 0, 0. Sorry, did I say 0, 0 or 0, 1? We assume that overall survival for all patients with the same covariate X is generated from the same G sub X. And we're introducing dependence on the prior for the family of the G sub X's by defining dependent atoms. And can you see the construction simply like this is exactly an ANOVA model where we have a mu sub h plus an offset if the first covariate is equal to 1 plus an offset if the second covariate is equal to 1, for example, if these were binary covariates. The important thing is that it's super easy. We could also include continuous covariates by having, say, I don't know, plus gamma h times a continuous covariate. But that's actually exactly what we did, and that's exactly what gave rise to the inference that I showed you. So this is all I wanted to tell you about the basic construction of the DDP model. I skipped many details, but I hope I got the broad theme of the construction. So this would be a good moment to ask any questions or comments or insights.
Peter,
yes.
can you hear me?
Yes.
It may be a naive question, but I would like to know if how you stop this sum. For example, you have some kind of series, and yes, I saw something like this also in the density problem. You have a series, but in practice you have to stop somewhere, right? Oh no.
So that question is about implementing, like actually implementing posterior inference in your computer. So we cannot we have a beautiful probability model now, the infinite dimensional guy, right? But you can't keep infinitely many point masses in your computer, right? Yes. So there's 2 answers to that. Let's first the cheap and easy answer. Remember the construction of the weights, we call it the stick breaking. In the construction of the weights, those weights are ordered in expectation, actually geometrically ordered. Like they're becoming very quickly, they're becoming smaller. So what we could do is we could simply truncate the sum when we have covered 99% of the probability mass. That happens very fast actually. So we might have only like 7 or 8 or 10 terms in the series. In terms of actual inference, in terms of actual pictures, if you simply truncate after 10 terms, inference looks almost identical to as if you were to use the full series. So cheap one, you can use what is known as the finite Dirichlet process just by truncating that series after a fixed number of terms. And because the weights are ordered, they're geometrically decreasing in expectation, you're not losing too much.
And this might vary according to the X, for example.
Oh, it could. Like, so if you try to do it, carefully, that you truncate when you reach a particular part of the total probability mass, it could vary by X. But even easier, you could truncate it a fixed, like after 10 terms. So now in some cases you might have 99%, in some cases you might have 96%. So either the truncation varies by X or the coverage varies by X. That is known as the finite Dirichlet process. That's probably the most common thing that is used for implementation. Alternatively, however, and that is not at all obvious, alternatively, it turns out you can actually marginalize in the inference, you can marginalize with respect to the atoms. Remember, at one moment we talked about how the atoms are linked with observations using these latent indicators. When we have 50 observations, we cannot possibly see more than 50 atoms, right? And typically, actually a much smaller number because the number of unique theta i's is usually much smaller than n. So if you only see like maybe 10 unique atoms, that means the remaining infinity minus 10 atoms we don't even see. So if we could analytically marginalize with respect to these other atoms that are not linked to actual data, then it also becomes manageable. And it actually turns out that marginalization is actually analytically tractable. I had one brief comment. Remember on one of the slides I told you that conditional on the F, the model for the thetas is easy because conditional on the F, the distribution for the thetas is simply product I equal 1 to n f of theta I. But then I told you it actually happens that in that model, we can actually marginalize out the F analytically, and it becomes a very easy model known as the Polya. So it actually turns out you can marginalize analytically with respect to those infinitely many unknown atoms and only be left with the at most n observed ones. Those are known as marginal samplers. We didn't talk about it at all, but that would be the pointed answer.
Also, I have a curiosity about the prior. This is not something that I understand very well. So let me ask you, how could you perform, how could you work if you know a priori that your function of interest have some feature such as a jump or some irregularity? How can you implement, how can you work on this in your prior?
Good question. Or even simpler one. In many cases, you might know that you might know some monotonicity. Like people treated at higher doses, the distribution should shift one way or the other way. Or you might want to assume unimodality or bimodality. You know, there's two subpopulations. Good question. Embarrassing answer. That is not straightforward to accommodate. So the question was, if you know certain features of the unknown distributions, is it easy to restrict your prior to those features, like monotonicity or change points or likely change points, things like that? That's actually not straightforward. Obviously, there are constructions to do that, but it's actually not straightforward, is the honest answer. Which is kind of embarrassing because we are talking about Bayesian inference. Part of the Bayesian inference is if you do have expert prior information, you should be able to use it. And you essentially called attention to the fact that there is important prior information that might not be that easy to use. It's unfortunately true. So there's no quick good answer. Any other comments? But those were good observations, yeah.
Thank you.
Peter, Stefano has a question.
Go ahead. Oh, sorry, it's in the chat or it's in?
Yes.
No, I guess he will speak.
Please.
All right, thank you. I'm interested in the wavelet basis for noise reduction in chaotic time series. And my question is about the impact of these methods in the noise reduction, and if you would suggest something to be applied to improve the regression.
Good question. So it's about I only mentioned it very briefly that we can use basis expansion of unknown functions to put the BMP prior on unknown functions. And one popular basis to use is the wavelet basis. And if I understand the question correctly, it's can we introduce some intelligent, can we use some good prior construction for the coefficients with respect to the wavelet basis that might help us in noise reduction? Cheap answer, any prior helps in noise reduction because it introduces prior shrinkage. So when you use any of these basis expansion, be it wavelets or any other, or whatever is your favorite basis, splines or whatnot, the basis functions, they are fixed, right? The random quantity becomes the coefficients of the basis functions. And in the wavelet constructions, those coefficients are known as the empirical wavelet transform of the data. So you could use just putting a prior on the model creates prior shrinkage, which helps in noise reduction. I can't really say much more about it. I mean, there are specialized constructions to introduce assumptions about dependence, like when you have spatial data, like when you have pixels, when I might index pixels, you might know dependence of the pixels, like pixels that are close to each other, you should have more dependence than pixels that are far from each other. You can actually set up priors for wavelet coefficients that allow for such dependence. Specifically for time series data, I mean, no good answers. Part of that is to my ignorance. It's not exactly my corner, yeah. So good question. I don't have a complete answer. Can you still use the? I actually still had one last example, but maybe we are slowly running out of time. Then let me just quick executive summary of the example. The example is about something known as dynamic treatment regimes. For dynamic treatment regimes, issues arise of causal inference because treatment selection is not always randomized. One way of adjusting for the lack of randomization in a clinical trial is something known as causal adjusting for lack of randomization is essentially causal inference. And one way to deal with causal inference is using what is known as potential outcome framework, which means we are trying to impute what the outcome could have been under alternative treatment assignments. And there it's important that your model that you use for the potential outcomes, that needs to be flexible, because you don't want the parametric model to drive your inference for outcomes that you could have seen but didn't see. In that case, so those of you who work with that kind of stuff, you know what I meant. Otherwise, it was way too quick an outline of the problem. But in such problems, we find BMP very helpful, and we think it does very well. So using BMP for potential outcomes in a causal inference framework, we think is a very promising direction. This summarizes a little simulation study. Where in that simulation study, the true treatment effect is that vertical black line, and the histograms which are smoothed out as curves. Each different color histogram shows estimated treatment effects under massive repeat simulation, where the light blue and the pink is just linear regression without adjusting for the lack of randomization. We totally misestimate the treatment effect. The blue and the green adjusting for lack of randomization using what is known as inverse probability weighting and double robust methods. They adjust for the lack of randomization, but they leave a lot of uncertainty. The red one is using BMP to impute potential outcomes, and it actually seems to compare favorably. Maybe that's all I should say without running over time. So that brings us actually then to the end of this. Thank you for sticking it out. Hope I gave you like some flavor of non-parametric inference. On the slides that you can download, Andressa might have sent them around, I don't know. In the end, you should see some references to more elaborate write-ups. It's still a thankful area. Like it's a good area to work in, but it depends a little bit what you're interested in, of course, in life. So thank you, everyone.
Thank you, Peter. May I ask you a very quick question? Maybe kind of related to what you talked today, but part of it is not what we're talking about. It's exactly about wavelets, because it's something that I like, but my formation it's a frequentist one. I'm not a Bayesian in essence, although I like it. So recently I have been reading something about, and the Berger-Müller prior, for example, is something that raises some interest to me. And this is something that, one thing that kind of makes me disappointed is that usually when you are working on these things, the errors must have some distribution a priori, right?
You mean the like if you model the wavelet coefficients, you're talking about the residuals in that model or something like that?
Yes. Just like you showed in your slide, you said it was not fully non-parametric, right? Because
I know what you mean. Like, let me go back to that. You're talking about this one here, right?
Mm-hmm. Yes.
Like, then you would so you would have a wavelet basis. You would have a wavelet basis to represent for a non-parametric representation of the F. Mm-hmm. But then there are the errors here. There are the residuals, and you're talking about these residuals in the regression model. Got you? Yeah.
Yes. Usually, it's assumed a normal distribution or something like that to develop the distribution, the posterior distribution of the wavelet coefficients. But this is the main difference that I see between frequentist and Bayesian analysis using wavelets. When I am using wavelets, in the frequentist setting, usually this error is not necessarily assumed to be a normal distribution or something like that, because you explore some asymptotic properties and you can kind of go ahead. But when you are in the Bayesian setting, usually this assumption is kind of imposed. Is it possible to work around this and do not impose an assumption to this error?
Good question. I mean, pointed quick answer, yes. Long answer, you're pointing out the kind of a limitation of Bayesian inference in general. We have to assume a full probability model for everything. Like if you don't just exploit asymptotics, but you want to work in a full probability model, then you have to specify a distribution for the residuals, and I see how you can be uncomfortable about that. Specifying a distribution for the residuals is equivalent to specifying a distribution for the empirical wavelet coefficients. And so your question is, could you go BMP on that distribution? So in principle, you could. I mean, nothing stops you from that. The easiest BMP model would be replace the normal residuals by a mixture of normal residuals. Even simpler, say a mixture of free normal residuals. That really wouldn't make it that different because inference under that model is almost the same, like a few more lines of code. And mixtures of free normals are already amazingly flexible, right? So in principle, it could be done. I'm not sure whether that's a promising direction, because if you go non-parametric on the mean function and non-parametric on the residuals, then what you have really done is you're going non-parametric on the distribution. Like the mean function plus the residual implicitly defines the f sub x. And like in that case, I would probably rather prefer to just focus on the f sub x. So a pointed answer, I think it could be done. Like the easiest solution would be replace a normal by a mixture of normals, and you can make it more sophisticated and make it a BMP mixture of normals. I'm not, but if you do that, like instead of putting a BMP mixture of normals on the residual, maybe you could just as well put in the BMP prior on the family of distributions. Same thing in different words. If you go non-parametric on the mean function as well as the residual, then there might be no more benefit to that representation. Like representing the distribution as mean function plus residual is meaningful if one of the two we assume a parametric model, right? In the extreme case, linear model for the mean function and normal for the residual, then we have the normal linear model, right? But when you don't make parametric assumptions on the two parts, then maybe there is no more motivation for representing it like this, and we might just as well just think about the family of distributions. But in principle, it could be done. I have never seen that, but in principle, it could be done. Maybe one thing that might really motivate it is like for the epsilon I, if instead of a normal, you just want to assume a distribution with fatter tails, you could try to set up a BMP model that allows for much fatter tails, like going beyond just the T. That might be meaningful, but I understand too little about that corner to really make an intelligent suggestion.
Yes, because when you are working with the wavelet setting in a Bayesian scenario where you consider, for example, the I don't know, Brandy calls it Berger-Müller prior. It's a mixture of a density with a point mass, and I think it's because of your work, right?
No, I don't recognize it. But I mean, what you say makes sense. Just a mixture of a density with a point mass, that's often a useful one. I mean, a point mass at zero and a density for non-zero, like just a zero enriched distributions are often useful. Yeah.
Yes, and when you work with this, you don't have to deal with MCMC. You have already the distribution. Of course, when you assume some distribution to the arrow. And then my point was exactly if this would be possible somehow to perform and avoid the MCMC and still have the fast computations and the sparse representation, etc., etc. You know.
I mean, in principle, it sounds attractive. Yeah. I mean, avoiding full posterior simulation is always a good idea, especially when you have like ever increasing sample sizes. I mean, it sounds like a reasonable idea. It's nothing I've ever done, so I can't really comment too much on it. Sounds like a reasonable idea. I wouldn't make it too sophisticated, lest it might be easier to just go fully non-parametric on the random distributions. Like, but as long as you keep some, like there must be some reason to keep this decomposition. Like if you're going fully non-parametric on both, then there's no more point of the decomposition. But if one of them is like more informed than the other, maybe, yeah. So it could be done. I just know too little about it to comment much more on it.
Okay, thank you.
Thank you.
Peter, if you have time, you have another question here.
Please go ahead.
Yeah, Rodrigo. Rodrigo has a question. Rodrigo, can you talk about it?
All right. I first of all, thank you very much for the presentation. It's always very interesting to see the developments on Bayesian nonparametrics. I guess I would like to get back to my original question. I am mainly interested in trying to build a credible interval for a prior process. In this case, let's say a Polya tree, right? And I feel like your suggestion is very much on the right track, since we generally use partially specified Polya trees to do modeling, right? But so maybe I would just need to worry about the partition points to build the pointwise intervals and such. What I'm actually having trouble with is actually how to build these intervals in order to ensure that my results are either densities or actually accumulated probability functions, right? I.e. that either they integrate to one or that they are non-decreasing. How can we build a credible interval taking these restrictions into consideration?
So maybe my approach is much more low-tech here than what you have in mind, much simpler than what you have in mind. I would like, when we're talking about credible intervals, you mean like, are you referring to pointwise credible intervals, like for a given x, a credible interval for the density at that x? Is that what you have in mind? Or like, I always find it difficult to actually represent uncertainty in the random probability measure, simply because the thing is high dimensional. If you reduce it to just pointwise credible intervals, I can think about it. Credible intervals on an unknown distribution in some more general way is something I would love to formalize better. The only thing that comes to my mind is pointwise credible intervals. And those are easy to do. Like in many of the figures I showed you, we generated like, I don't know, 100 posterior draws, and I showed them as the gray lines. And then at each point, you can just, if you have 100 posterior simulations for a 90% central credible interval, I just look for the lowest 5% and the highest 5%. And that defines in between the 90% pointwise credible interval. But I think you have something much more structured in mind.
Yeah, it's mainly because I want to build some sort of abstract region and see if different functions are, different curves in the sense, are inside this region or not, so that I can build some sort of test, I mean.
Makes a lot of sense. But so you're actually really talking about credible intervals for the entire function, not just pointwise.
Yeah.
That is obviously a right thing to think about as a notion. I find it difficult, like to start with that, like to start to talk about intervals, we need some notion of a distance, right? So we need a distance between functions, and then so in principle, if you for a given distance, whichever one you choose, in principle. So numerically, we could probably pin down credible intervals. Like I would just simply define them as balls with respect to their distance. Like take the posterior mean of the unknown function, and then balls with that with respect to that distance I could use to define credible intervals. I've never seen people do that, although it's like the way how you mentioned it, it sounds like a reasonable construction, yeah?
All right.
So we can think about it, but it's almost impossible to show it, right?
Mm-hmm.
Because then I have a credible interval in the function space. How do you visualize it? I'm just talking about creating a plot. Yeah?
Right.
That's probably the simple reason why I've never seen that. But like you have obviously in mind an application where you can use such things to implicitly construct tests, right? Like credible intervals, then I can construct obvious kind of tests. Makes sense. And you could choose a distance function that somehow focuses on the features that matter in your application. Makes also sense, yeah.
Correct.
In the case of that survival data with the 700 patients in the breast cancer study, we could try, like for example, we could answer the question: is there a difference between high versus low dose? And then we would just one could look for credible intervals and see whether they overlap, right? I assume that's what they have in mind.
Mm-hmm. Right.
Okay.
All right. Thank you very much.
To finish, Peter, we have a comment of Professor Josemar Rodrigues here in the chat. He says that it was very nice to see you here. And he just comment if you think about Curry rate models from the regression G.E.P point of view.
Sorry, which models?
Curry rate model.
Pure rate models, got it.
Pure, yeah.
Nice to virtually see Josemar again. We met very first time, I think it was in Sao Paulo. We met long time ago. Probably it was something at UFSCar. I don't remember what it was, some conference or workshop.
Yes, probably it was in UFSCar, and now here he's in UFSCar from São Carlos now.
I remember at one time there was an E-Levy in Sao Carlos, and I was there. And I think we actually went at one moment in the afternoon. We just went over and he showed me UFSCar Sao Carlos campus. So I know there's an UFSCar campus in Sao Carlos. For Q-rate models, it makes a lot of sense. So Q-rate models, it's kind of related to someone else brought up the notion of zero-enriched, like putting a pointless at zero. Q-rate is about with some probability. Sorry, it's related in an abstract sense, but so specifically it would mean that with some probability we don't see the event at all. So for overall survival, that's of course a bad example because we all die eventually. But for time to recurrence, that might be a good example, because time to recurrence, well, for the ideal patient, there is no recurrence. The thing does not come back, right? And then you might want to introduce positive probability atom at infinity for not coming back. Very sensible construction. I mean, that would lead one to introduce an additional layer in a hierarchical model, right? Like I would first, like I would just build a hierarchical model there. First, with some probability, you don't observe it at all. That's the cure rate. And with remaining probability, we observe the recurrence, and then we can have a BNP prior on the survival function.
Thanks, Michelle. Would you like to finish?
Okay. Well, I think we are. It's a little bit late. The short course by Müller was a success, I can say that. And I would like to thank you, Peter, once again for kindly accept to giving us this short course today.
Well, thank you. Thank you for the opportunity to present here. It's always a pleasure. This was a super easy trip. I still hope that the next trip will be more complicated and in person, yeah?
Hopefully.
direction or the other. So thank you, everyone. Thank you for joining. And
Thanks so much, Peter.
have fun with PMP. Nice to see you, Diane. Yeah.
Oh, nice to see you. I hope the next time you'll be in person.
Oh, either in Austin or elsewhere. Yeah.
Yeah.
Are you coming to Montreal? That's the Montreal is like the big biannual Bayesian statistics meeting coming up.
Oh, yeah.
Including there's a famous Brazilian Bayesianist there, Alex Schmidt.
Oh, yes, yeah, yeah. Great.
Well, thank you.
Thank you so much.
Thank you, everyone.
Peter.
Bom dia. Bye. Thank you.
Bye, bye. Bom dia.
Bye-bye.
Tchau, tchau.